So let's talk about when we have stride 1, this is 3. When we have, then we move rightward, right, after computing this, and then we store -1. Similarly, we move 1 right hand side, we store that value, the dot product, -3. So as you can see, right, at this location, this is -1. So that will be -1. -1 is here, -1 is here, and we have 1 and 1. So that's why all these 3 entries will lead to 3 -1, and that's why we will have -3. All the remaining dot products are going to be 0, and that's why, the overall value at this, after output, after this convolution operation at this specific location is going to be 3. So this is what we are going to conduct. So again, we will compute this one, then we will move down. Okay, so we moved here, and then we move down, and we keep doing the dot product, which is the convolution operation. And in that case, we will get -3, we are going to be storing. And similarly, we move rightward, then we come down, we move rightward, and we store all the entries. And this is the output of the convolution operation if this is your image and this is the filter that you have, right? So this is the main meaning of, the overall convolution operator. And then at the last stage, you will compute this, the convolution of this portion of the image with the filter, and that will be stored as a -1 value in the overall operation. Okay. So now, you can see that there are different patterns that you can identify, and where the filter, where it has 1, you can see that there are matchings at certain location of the images, and those you will have essentially higher values on those locations that is there. And this is what we want to capture. We want to capture whether we have those features inside the overall image or not. Okay. Now, rather than having a single filter, you can essentially have multiple different features, multiple different filters that can simultaneously operate on the overall image that you have. So right here we have filter 1. Similarly, what we can do is we can apply the filter 2. So if you look into the previous image, this filter had different entries in the rows and column than what we have in filter 2 right here. Okay. So we can also do the convolutions with filter 2, and we can store those values, right? And this is another idea where the number of filters that you use in the convolutional neural networks could be different, and that's also a parameter that you can set, and that helps you in essentially understanding or recognizing different types of features that might be present in the overall image that you have. Okay. So if we have this feature, what we do is for a second filter also we'll repeat all the steps, which is basically doing the convolution of this filter with the image at this location, then move here, this location, and keep doing that, and storing that value will essentially help, right? So for the second feature, if you do the convolution, then at the specific locations of the images, you will get these values. Now, if you do these computations with the filter that we have on this slide, the values at that location are basically, after the dot product are listed, what you see we have here. Okay, so we can keep going on, and similarly, in the final location, we can take the convolution of the filter 2 with the image, and that will be also stored here. And as you can see, this is the only portion in the image where we have 1, 1, 1 vertically aligned, and that is matching with the filter that we have. So that's why we have a large value at this location. Okay, so again, there are multiple things that I want to summarize. First of all, filter, there is a convolution operation, which is a dot product. There is a stride. So the amount of movement that we are doing between each convolution, and we are storing. And the third thing is that we can have multiple different filters that are going through the same images. And for all different filters, we will have different computations that we are essentially storing in the convolution network. And this stored value after convolution, whatever we are storing here, is essentially known as feature map. Okay. And this is the output of the convolution operators that we will get. Okay. So again, you can see what has happened. We have a 6x6 images, but when we do the feature map after the convolution operation, we essentially use 2 different filters, filter 1 and filter 2, and the output of the feature map, or the dimension of the feature map, will be 2 images, one for filter 1 and one for filter 2, but the size of the images will be 4 times 4, because we are taking this convolution operation. So you can see the size of this image after transformation to the feature map has reduced to 4x4, and since we have this 2 different filters, so the overall output of this process will be 2 times 4 times 4, and that's the number that we'll be storing as an output of this convolution operator on this image with respect to the two filters that we have. Okay. Again, so typically the images are not going to be white and black and white, so you will have essentially RGB image, and this is something we have discussed in the image representation. So you will have three different channels, and again then you can essentially apply two different filters on those channels, okay, and that will lead to a feature map. So the size of the feature map in that case is going to be different. Okay. So what I want to talk about here is typically when you have an image and when you are applying these two filters after convolution, the number of size of the feature map is drastically reducing. Whereas when you have a fully connected network, right, where everything is connected to everything, you do not reduce the size. The number of edges in this case are typically going to be higher than what we have. Okay. So this is the main difference. So the number of overall parameters that you have typically in CNNs are going to be smaller compared to fully dense deep neural networks that we have. Okay. So again, we applied this filter and we got this value of 3 at this, and the way to visualize this is like we have the overall, if we flatten this image, we'll get the number of this vector, and what is happening in order to compute this 3, we are only using some specific portion. We are only using these 9 features, right? Those are located at different locations to compute this 3. And then if I take different other inputs, for example this input, right, where we have -1, so even in that we are getting input from 9 of the input vectors that we have. So we have not connected everything to everything, which is typically there in the fully connected deep neural network, and here you can see that the connections are sparse compared to what you have in the fully connected deep neural networks, and that leads to fewer number of parameters, and fewer number of parameters means the computational time and the training is going to be smaller compared to the deep neural networks that we have.